Hello, everyone. Good afternoon. I am Dae Jung from KAIST, and I'm going to present the work, Razzer. Okay, Razzer, how to better find the race bug through fuzzing. This work is a joint work with KAIST, Seoul National University, and Purdue University. Kernel vulnerabilities have a very important meaning in system security because a kernel has the highest privilege. If the kernel vulnerabilities is compromised by the attacker, then the attacker may control the entire system. So fuzzing would be one of the most practical approaches in finding such vulnerabilities. While there are many different details and techniques in fuzzing, overall, most of them are coverage-guided fuzzing. Coverage-guided fuzzing gathers interesting inputs that extend the code coverage, and since more code coverage during fuzzing typically translates to more vulnerabilities, coverage-guided fuzzing appears to be very effective to find vulnerabilities in the target program. Using the fuzzing techniques, our research starts from thinking about how the fuzzing would work for race bugs. Before answering the question, please let me introduce the basics of race bugs. To easily explain our work, I'm going to assume that a race condition occurs between two threads. To have race conditions, the following three conditions should be satisfied. First, two instructions access the same memory location, and second, at least one of them is a write instruction, and third, two instructions are executed concurrently. Here, the important point is that if race occurs, then the computational result may vary depending on the execution order of instructions. It is very hard for developers to think about all possible execution order. Developers may fail to avoid the race condition, or they mishandle the consequence of the race condition. Therefore, a race vulnerability is caused by the execution order, which is unintended by developers. So, especially for the race bug, how would fuzzing work? Would it be efficient, similar to how fuzzers are discovering non-race bugs, or would it be inefficient? My short answer is that traditional fuzzers are not really efficient to find race bugs. This is because the race only happens if the offending instruction is executed within a specific time window, which we call as race window. Such a race window are pretty narrow. The traditional fuzzers are not really helping to make the execution happen within such a narrow race window. More specifically, the execution orders are mainly determined by the kernel scheduler, which is not considered at all by the traditional fuzzers. To better explain this, let me take the example, which is the simplified kernel race bug. In this example, there are two different threads. Thread one is trying to clone the file name object, and to do that, it first computes the length of the given file name, and it allocates the buffer using the length of the file name. Then it copies the original file name to the newly allocated buffer. But during this cloning process done by thread 1, what would happen if thread 2 modifies the file name object into a longer one? If the file name changes in the middle, then the size of the allocated buffer would be smaller than the size to be copied by string copy function. Therefore, buffer overflow would happen since more data would be copied than the size of the allocated buffer. To make the concrete case showing how inefficient traditional fuzzers is to find race bugs, we performed a restricted experiment using seed caller, which is the kernel fuzzer developed by Google. In this experiment, we tried to give as many favors as possible in finding races. We limited a set of syscall to easily trigger the race and limited the parameters so that it doesn't need to try that many combinations of syscall inputs. With these restrictions, syscaller failed to find all of 3 race bugs in 10 hours. As I will show you later, our Razzer found all of them in a very short time, from 7 minutes to 30 minutes. Now, to efficiently find the races, we introduced Razzer. The key idea behind our Razzer is not only extending code coverage for fuzzing, but also considering the thread interleaving to deterministically discover the race by enforcing the execution to be performed within the race window. To better understand this idea, let me take the example again. As you can see here, 2 threads are about to execute the previous example. But before executing the example, Razzer inserts 2 breakpoints at the end of the race window. Now, when each thread executes a syscall, each thread will stop its execution right before the breakpoint. At this point, Razzer ensures that the modification of file name by thread 2 is now performed. This means that modification of file name always takes place within the race window, so Razzer deterministically enforces that the race always takes place. Then we resume the execution of each thread, so buffer overflow always occurs. Again, this is how Razzer tames the non-deterministic behavior of race conditions, which in turn significantly improves the fuzzer's efficiency in finding race bugs. Now, let me start showing a little more design details of Razzer. Razzer consists of static analysis and online fuzzing phases. Razzer's static analysis identifies the location of the candidate to install the breakpoints by over-approximating data races. Then the next online fuzzing phases use the over-approximated data races and make the race behavior deterministic. Let's look at the detail of each component. And I will start with the static analysis. Razzer's static analysis identifies instructions that may race at the runtime. This is actually teaching Razzer where to install breakpoints to trigger the race condition. Looking at the technical details, Razzer's static analysis is inclusion-based points-to analysis, which is also known as Anderson-style points-to analysis. The static analysis certainly has both positives, as it is a well-known limitation of points analysis. However, this is not a real problem of the Razzer, because Razzer is doing the fuzzing in the next phases, and fuzzing technique itself does not have any of false positives. This can be an interesting feature of Razzer because Razzer takes the advantage of fuzzing to address the false positive issues of static analysis. Going back to the example, our static analysis will identify following 2 race candidates. One candidate will be between string length function and string copy function, and the other will be between 2 string copy functions. According to our static analysis over the entire kernel, we identified about 3 million race candidates. Based on these race candidates, Razzer starts fuzzing. Now, I will move on to the first fuzzing phase, which is called single-thread fuzzing. It is in charge of extending code coverage as well as finding an input which has two syscalls that can hit race candidates obtained by the static analysis. Razzer's single-thread fuzzing is similar to the traditional fuzzer. It basically runs with a single thread and makes an input while extending code coverage. Meanwhile, Razzer also checks whether two syscalls executed any race candidates obtained by the static analysis. If it found any, then Razzer transforms this single-thread input into a multi-thread input. For instance, saying single-thread input has two syscalls, open and rename. And we split this into multi-threaded input like this. Now, open syscall will be executed by thread 1, and rename syscall will be executed by thread 2. Additionally, we also mark the information about where to set up the breakpoint. In this case, it will be these two string copy functions. The last component of Razzer is multi-thread fuzzing. Multi-thread fuzzing will execute the multi-thread input generated by a single-thread fuzzing, while ensuring that the offending instruction is executed within the race window. So now, when running this multi-thread input, we actually install the breakpoint using the hypervisor. To do that, each thread invokes the hypercall. If the execution really stops at the breakpoint, then we perform the virtual machine introspection to see if the race truly occurs. That is, we look at the concrete addresses that these two instructions are accessing and see whether they access the same memory address. By doing this, Razzer deterministically triggers a race condition. There are a bit more details on how actually triggered the crash out of this race, but let me skip the details because of the time limit of this presentation. So now, taking about the implementation, we implemented static analysis using SVF, which is a static analysis framework based on LLVM compiler suite. And our single-thread fuzzing and multi-thread fuzzing is implemented based on syscaller, which is a popular kernel fuzzer developed by Google. The key changes is in implementing deterministic scheduler, which is implemented using QEMU and KVM. This exposes hypercore interfaces to support per-core breakpoints. Using these implementations, we fuzzed a Linux kernel about a month, and we found 30 new race vulnerabilities. Out of these findings, many of them have serious security violations, such as heap overflow, and user after free and heap overflow and double free. Lastly, to show how Razzer can improve the bug finding ability compared to the traditional fuzzer, we ran both of syscaller and Razzer with three already known race bugs. As I showed you before, syscaller failed to find all three races within 10 hours, but Razzer found all of them within a very short time, from 7 minutes to 26 minutes. So here, I want to emphasize that taking a considerable timing can make a huge improvement when finding race bugs. To conclude the presentation, we introduced the Razzer, which is a new fuzzer focusing on finding race bugs. The notable feature of Razzer is that it tames the non-deterministic behavior of race conditions by implementing deterministic scheduler. We combine well-known techniques such as static analysis and fuzzing to implement Razzer. And lastly, we will make the source code of the Razzer on the site on the screen. And thank you for listening, and if you have any question, feel free to let me know. Thank you.
We have time for questions. Please step to the microphone and state your name and affiliation. Going once. I think Giovanni has a question for this talk.
Never do this with Niels. I have two questions, actually.
Okay.
The first one, it seems that you're taking one thread, so one piece of code, and then you split it and you make sure that two threads are executing the same code. But do you also consider threads that are executing different parts of the code, but they actually share some of the data?
Pardon? I'm sorry, I don't understand. So could you please repeat it?
Yes.
Okay.
So from your explanation, I haven't read the paper, so you might explain this in the paper, I'm sure. But you have sort of like execution of certain instructions. And you can see if I take this piece of code and I have two threads executing the same code, I might have a race condition. However, you could also have situations in which you have two different pieces of code that are executed by two different threads, but they're still creating a race condition. Does your tool take care of this?
Yeah, of course, Razzer take care of the two different codes have a race condition. Actually, I said that there are two syscodes in the sequence of syscodes. So we split it, and then the two syscodes are executed in the different thread. So it means that two syscodes have different code. Two syscodes execute different code. How to say that?
Yeah, take your time.
All right.
No pressure.
Thank you.
No, seriously, take your time. I don't want to. I know it's hard to be there when somebody's asking questions.
All right.
With language barrier and all that. Oh, author. To the rescue. Go.
I'm the co-author of the paper. So we are basically running two different code in the two different threads. So given the same code, we are actually splitting up into two different code. We are partitioning the code, and one partition is running one thread, and the other one is running on
that. I understand. The point that I don't understand, there was somebody else, so I'm going to be very short. The part I don't understand, suppose that I have a race condition that is not caused by two threads executing the same code with different timings. But actually I have two threads executing two separate functions that for some crazy reason got as a parameter the same object, and now there is a race condition. Do you deal with this case?
So yeah, even if it is running with the same code, technically we should be able to handle that. Because what we are doing is that we are simply running the single thread code, and if it is actually making the same syscode, and if they are actually accessing the same data variable, data address, then we're going to actually split the two into two different threads. So technically it's going to handle, but we haven't checked it.
Okay, in that case, I would challenge your over approximation soundness claim in that thing.
That's true.
Hi. One last question.
Hi, this is Shin Yang from Microsoft Research. And in your talk, you mentioned that you use a breakpoint to verify that this is a true race condition on two threads. So if one thread hits the breakpoint, but the other never hits the breakpoint, how do you handle this situation?
To make sure that thread 1 hit the breakpoint and thread 2 doesn't hit the breakpoint, right?
Yes.
We think that this is possible when the code instructions are protected by a lock. Then if let's say thread 1 hit the breakpoint, then thread 1 hold the lock, and thread 2 cannot hit the breakpoint because of the lock. So we installed a timer, and after the timer expires, then we think the two instructions never race because of the lock, so we discard the input.
I see. So you have a timeout mechanism to handle.
Yeah.
Okay, thanks.
All right, let's thank the speaker.